So just to summarize, we acquired image using some quantization sampling. Okay, and then after that, the image was actually a set of pixels, right, that has some dimensions. And after that, we said, okay, let's what to do with the image. So if you have a light, different type of light, dark image. So how to make adjustment? So in last lecture, we saw that we can do a point processing, but we have some limitations for that methods. Okay. One was that it requires a lot of user input. Okay. Although it was easy to implement, but a lot of user. So we are moving towards some augmented methods, and one of them is now histogram processing. So still we are doing spatial domain image enhancement. In this set of slides, we will talk about histogram processing. Okay. Here are the content. So what is histogram? So histogram are the nothing but just the number of the pixel inside the image, or number of the samples inside the image, or any set that you have. But since we are talking about the image processing, so number of, let's say here you have these are the number of pixels for the level R1. Okay, let's say you have one level. One level has 8 pixels inside an image. Okay, it cannot be like at the same part, but it can be separate. Then 2 has 4, 3 has 3 pixels, 4 has 2 pixels, then 5, then 6, and 7 and 8. So it's just an illustrative way of defining it, that these are the number of pixels inside some set, or in our case, it's image. So this is actually histogram. If I just plot it, the intensity versus the number of times it's repeating. Okay, this is histogram. Nothing else. Anything difficult? Yeah, we will discuss this one. Let us define the histogram function first, and then we will see that what benefit it is giving to us. Okay. So this is again a practical example. You can see that this is an image. So how? Yeah. So of 3 bits, we have intensity level from 1 to 8. So 1 is repeating how much time? 1, 2, 3, 4, 5, 6, 7, 8. Okay. So 8 times. Okay. And 2 is 1, 2, 3, 4. Okay. 3 is 3, 2 and 4 are like this. Okay. So if I want to plot it, how I can plot it? This is just an illustrative way, right? So how to plot it? So we have 1, which is 8, right? Okay, then we have 2. 1, this is 2, 3, 4. Okay, so this is 4, this is 3. Okay, so if I want to plot it, I have the levels, the intensity levels here. Okay, and here the number of times it's repeating. So this is the program. So okay, sometimes program, let's say you have 2 images. One is bigger image than other image. Okay, so you cannot compare, because the maximum for one might not be the maximum for. Okay, so we have to normalize the histogram in order to compare the two. Okay, how we can do that? We normalize by number of pixels, n are the total number of pixels. So in this way, the maximum in a histogram can be 1, 0 to 1. So it means I normalize it, I can compare to in a good way. Okay,
but the same shape was taken with like 4 megapixel and 12 megapixel camera.
Yeah, but if let's say if you plot both on the same curve, so you cannot compare. One will be like bigger because you have load, so the other will be smaller. But if I just normalize it, it will be between 0 and 1, so I can compare. Why the comparison is necessary? We'll see this. Okay. Okay. Now the sum of the So this is now every point here. If I divide by how much we have now? Sorry, divide by 4 by 5. Okay. So 20, right? 25 by 5, 25. So if I divide by 25, so it will be just a portion of 25. And if I sum that up, what I will get? 0.1. Okay. So this, what is this actually? This is the probability of pixel k or rk. Okay, this is the probability. Let's say for the probability of 1, I will just divide this 8 by 25. This is my probability of pixel 1 in the end. Okay, and sum is 1. So if I do the same thing, I will get the probability for the first pixel, second pixel. We get the whole probability. If I just sum them up, I will get 1. Okay. Okay. Now, so what we did, either we can have an unnormalized histogram where we just have the number of pixels, or we can have normalized. This is what we did, and sum is equal to 1. Okay, histogram gives a very good, I will say, idea or indicators of low contrast or high contrast image. So we'll see this in the later example. Okay, then if the contrast is low, it means that the histogram will be different as compared to when the contrast is high. And here it comes to what we do with the histogram. The question, the answer will lie here. Okay. Okay, we expect that an image whose pixel density occupy the whole range will have what? Let's say if the histogram is equally distributed. What do you expect?
All pixels have the same color. Just fine.
Yeah, identically the number of pixels belonging to specific intensity.
Like that is more visible and like.
Okay, in other words, let's say if the histogram is concentrated towards the and towards the 1 or 2 or 3 pixels. Okay, I will give you more examples.
So if I have a picture that has all pixels,
that means that it is equally divided, and we have the pixel from various values, intensity values. So contrast will be high. Yes, a particular intensity level. Each pixel, yes. So it means that this is equally progressed. Okay, let's see. Okay, see this very good example. This is the dark image, right? So see, this is before anything. Okay, any processing. So this is more darker, right? So all the pixels are grouped here, right? What about this more bright? This again in the middle, it's in the middle of that, but again the contrast is also very low because all the pixels either belong to these locations, they're not equally spread. Okay, so what about this one? There's good contrast. You see this? Okay, so what? Now let's see. In the previous lecture, we were trying to make the darker image brighter or brighter image darker. So we have to define the curve, either the power law or the rule. Okay, this is what we have. But here, if I try to make any image, this image or this image as a flat pixels, try to distribute it flat, I will get, if I input is this, again I will get this, even if I just make it uniform, right? If I get input as this, output will again this. If input is this, output will this. So it means that histogram is automatically adjusting the contrast. Okay, so this is the good thing about histogram, right? Now how it's been done? We have to talk about it. Okay. Okay. So see, for all these 1, 2, 3, 4 images, I applied the histogram processing, or I call it histogram equalization, which we'll discuss later on. And what I get for all these three, darker becomes again good, same. This becomes again the same. Okay, and this again, and even if it was equalized, it's again the same. Okay, so what we are getting, whatever the image is, yeah, so you get the more contrast image or balanced image. Okay, this is here. Now the question will how? Okay, so we can discuss this. So anyhow, the method that we will use is called the histogram equalization, which use the histograms. Okay, and basically what we did, this is again a low contrast image. I'm trying to spread the pixels evenly, like I'm trying to be uniformly distributed. Okay, so if I do this, you get very good pixel. Another example, this is another example. Okay, very dark, become very good, very contrast is becoming very good. But make sure that I will not be able to make it 100% uniform. Okay, I cannot make it 100% uniform because there is some ratio of the pixels that are more than others, so I cannot do it. But I will try my best to spread. In other words, I'm spreading the energy equally. Okay, this is here. Okay. So in order to go to the histogram, we have to understand PDF. What is PDF? Density function, which we already have seen that it's nothing but just take specific pixels dividing by total number of pixels, and if I just do it for all the pixels, this is my PDF. Yes or no? Okay. So let's see. Let's see. You have 4 pixels. So you have 0, you have 1, you have 2, and you have 3. 4 pixels, right? And if that is the okay, let's call it ZK. Okay, this is ZK. So let's say if you have this has a probability of 0.2. Okay, this has a probability of, let's say, 0.3. Then you have again 0.3, and what will be this? 0.2 to make it 1. Yes. So this is nothing but PDF. In case of continuous, it should be continuous, but in case of the same, also call it probability mass function. It's the same. Okay. Now what will be the CDF? Okay, so it will be at the start. It will be 0.2, then 0.5 and okay 0.8 and 1. Okay, so this will be 1. So this is PDF, this is CDF. Okay, and we can define it like C of ZK. So this is PDF and CDF. Yes or no? Okay, so now if you understand these two things, let's move forward.
The PDF is just stating the probability for every.
And which is histogram, normalized histogram. So PDF is actually normalized histogram. Okay, I think this already we did it. Just this, and CDF at any point I can define it like the PDF from 0 to that point. Sum of PDF from that point. Is this clear or not? Simple, right? And summing up, it's already sum, right? So CDF at any point that K is actually from the 0 to K. For 0, it will be probability at 0. For the maximum L minus 1, it will be 1. Okay, because I'm summing all. Yes or no? Yes. Okay, also I can denote it by this as well. P of Z less than equal to ZK. Z is actually given number. Okay. Are you absorbing it or not? Yes. Okay. Anything difficult? No. Okay. So what we talk about the histogram. Histogram is same as PDF. PDF and CDF is accumulated stuff. That's it. Okay. This is what we did up to now. Now see, let's say I take an image. This is my PDF. Okay. This it's discrete, but because it's been plotted like this, so it look like continuous. If I plot the CDF, it will be goes to 1. Yes. Okay. Now, if you recall, last class we had a transformation function. Okay, which was either the power law or log. Okay. So if you see this one, it's very similar. Yes, it's very similar to that transformation. Okay. Now, if let's say if I want this curve as a transformation, and I will tell you why I want to use it. If I want to use this curve as a transformation function, so this is the input and this will be the output. Okay. What I'm doing is I'm using CDF as my transformation function. Okay. So this is my input and this is my output. But there's one problem. Input goes from 0 to 255, but output should also be 0 to 255. But this is from 0 to 1. Okay. I just multiply with 255. This one to make it from 0 to 55. Now let's say this is my transformation function. Okay, and if I apply this to this one, I get some transformation. This image is transformed using this CDF as a transformation function. Okay, so if I plot a histogram of this one, this histogram was this, means that this is not a flat histogram, right? Which I want. But if I plot a histogram of this, I get very flat. Yes or no? It means that if I use CDF as my transformation function. So I get almost like a flat or uniform. Removed it, but I don't know. Okay, let's move on and see what's the reason. So I think I want to explain here. This is a data, right? Okay. If I plot a histogram of this is this, and if I plot the CDF, it has a CDF here because the sharp here because of more probabilities here. Then this is the brighter, so we have the sharper or the slope here, maximum slope here. Otherwise, it's not right. Here is this, right? It's there are more pixels in this location, and in this the CDF is very flat. So one thing is right here that if the image has a more contrast, the CDF will be a kind of a linear. This is the confirm. Okay, this makes sense as well. It's linear. Okay, it has the flat CDF. PDF. Okay, so now see these curves. If you have more intensities at the lower side, it will be sharper at the lower side. Okay, at the beginning. So if I use this as a transformation function, what I'm doing, I'm basically making these pixels brighter because of the sharp. I'm making this brighter, which is what I want. Yes or no? If the slope or the curve is like this one, it means I am making these pixels towards the darker side. So that's why it makes sense. See what I'm saying? Because of the CDF nature, it's working. Yes or no? Yes, yes. Okay, so it is actually the nature of CDF that makes it work. Okay, why? Because if we have a darker pixel there, it means that the CDF curve will be like this. If we have a more brighter curves, it will be like this. Okay, delayed. So if I use this as a transformation function, what I'm doing, I am making the darker pixels brighter because of this curve, nature of this curve. And this curve nature shows that if I use this as a transformation function, I'm making the brighter as a other. Okay, now mathematically, how I can write it down? What is the transformation function? This is S and this is R. Okay, this is the transformation function. This is the input intensity and this is the output intensity. I'm transforming this to this. So what will be the equation? If I want to do it on paper, I need an equation, right? So the equation is simple, 1 L minus 1. What I did, I multiply CDF with L minus 1, if you remember previously. Okay, so this is S. So S equals to L minus 1 into CDF. So if I just try to do how to map it, I take any R, put it in this equation, and I get S.
So on that point, let's say we take 100. It will be 99 times the value of the CDF at 100.
Yes. Okay, and how to find the value of CDF at 100?
Just accumulate it and
yeah, so you need PDF then, sum of PDF. We have the formula, right? For the CDF, we saw the formula. So it's just sum of all the probabilities from 0 to 99 or 0 to 100, 0 to 100 actually. Okay, to get that. Okay, now still the proof is not there. I did something. So this is actually histogram equalization, this equation. Yes or no? If I need to find S for any R or V, in here we call it V, but we just have to sum the PDFs and then find S. Yes or no? Okay, now it's okay.
So why we need to have L minus 1?
Yeah, so why we have again we have to go back and see why we have that. So this was the function CDF.
Yes.
But here I said this is from 0 to 1. Yes. Okay, I want to transform 0 to 255 to another 0 to 255. So this is 255. It is L minus 1. Okay, so I multiply L minus 1 multiplied by CDF. I get the transformation formula. Okay, now so our aim here is PDF to a straight line PDF, which is we call it uniformly distributed. Now it's some logical sense of it and we derive it. The method is what I told you. But we still need to find out that why can I prove that mathematically can I prove that the PDF of S, which is the transformation, is actually uniform. So for that I have to take a continuous case because discrete case I cannot prove. Okay, so continuous case is what is just like a continuous signal. So I have any PDF and I want to transform to this, and I want to prove that once I transform, it has the flat PDF, which is uniform PDF. Okay, for that, and I use this transformation function. Anyhow, okay, this is some of the proof which is actually is not included. I just put it just to make sure that if you are interested, you can look into this. But I am interested only in this. Let's say you have a PDF of X, and I want to convert that PDF of X to another PDF, which is Y. So this is the relationship. Okay, from where it comes up? It comes up from the probability theory. So if you are interested, go over it. If you are not interested, it's okay. Just look into this. Yes. You cannot. No, but we cannot have it because flat means that all the pixels must be of same, I will say same number in the pixel. If we make it, yes, we will lose some information. Yes, okay. So is this clear? In order to move from PDF of X to PDF of Y, what I will do, I will just take a derivative of X with respect to Y to take that absolute basis. X and Y are two variables. Okay, just this general expression that if X is a variable, Y is a variable. X is a PDF of P of X, Y have P of Y. I want to convert PDF of X to PDF of Y. In other words, in our case, it was, let's say PDF of X. I want to convert it to PDF of Y. How to do? Yeah, I should be informed in our case. Okay, but it is a general expression. So any distribution to any other distribution. So I have to find the derivative of X with respect to Y. Okay. Now what it means? Yeah. Yes. Okay. Now
two functions has nothing to do with this. Now we want to get PDF of Y from PDF of X.
So what?
It has no relationship. Just somebody in Korea, somebody in Saudi. So what's the relationship?
Relationship is there is the relationship. That's why I'm saying that don't go. If you want to go in detail, this is the relationship. All the derivation is there. Okay, but because it will take us away from our topic, so I don't teach that. Okay, so let's take this one. Okay, I want to let's say probability of R or the PDF of R, which is our original image. If I want to change it to another one, probability of S or PDF of S, I just make the multiply the derivative of R with respect to S and take the absolute value. It's the original distribution, and S will be the transform distribution, which will be the uniform. Okay, now the same transformation that we did for the discrete case, in continuous case, it will be like this. Agree or not? Because the sum in the discrete is integration, and I should integrate from 0 to any variable R. Okay, and because it's transformation of R, and then this is the probability of original PDF of R. Now, if I just now I need to find ds by d, dr by ds, or I have s, so let's say ds by dr. If I differentiate this one, what will you get? Differentiation of this term, this will be cancelled out, so I just get the probability. Okay, if I put here to the original equation, what I will get? This is 1 by L minus 1 P of R. So this will be cancelled out. So what I get? This will be cancelled with this one. So it means that the PDF of this is this. And what it shows, so what I did, I took that expression that we derived for the histogram equalization and tried to find the PDF of S using this expression. This is what I did. So once I find it out, I got 1 by L minus 1, which is a flat PDF. So it means what we were doing, once we started with what? We just started with CDF. We said, okay, let's take it as a transformation. This is what we did. But with that transformation, I proved it that this PDF is flat. It's okay now. CDR by ds. But I took the S and take the derivative of this with respect to R. This is what I did. Once I get the derivative, I put it in the same just to find out the PDF of S, because I know the PDF of R. Okay, but here it's been cancelled and all that. So it means that whatever is the probability of P of R, what is the PDF of R? Regardless of that, you will get L1 by L minus 1 because it's been cancelled out. So this is PDF of the original image, and I want another image that should have this PDF, uniform PDF. Okay, and the transformation in between is how the CDF. I transform this to the C.
Now we have a picture of Hassan with this like PDF. Now I want to unify that. Yeah, sure. And then I process the image to have it like with the uniform PDF. Now, now what we have done is just through the CDF, it's just mapping between the CDF. Now all that is just jumping,
I wanted to prove that once I did this transformation, I will get this. This is what I do. So what I started with, this is the equation that I use for transformation, right? So I use this equation for a transformation. So now I want to find the PDF of S, which should be applied. Okay, so I want to find the PDF of S. How I can find the PDF of S? I will take the PDF of R, because PDF of R is my original image, which I know. Okay, so for this I use this equation for transformation. If I want to go from R to S, the PDF of R is multiplied with derivative, and then it will give me PDF of the transform image. Okay, so in order to find that, I need dr by ds. So I can find this here. I differentiate S by R, ds by dr. So once I do that, I get this equation, which is nothing. I did not solve anything. Derivative cancel with integration. That's it. Okay, I get a simple equation, right? And this equation, when I put it in the original one to find the PDF of S, I get L minus 1, regardless of what was the probability of the R. The PDF of. Okay, let's do some example. Hopefully, you will understand. Okay. Again, since what we said, whatever PDF you will have, the original image, it will give you 1 by L minus 1. And let's say you have been given the PDF of the original image, okay, which is continuous image. If I just want to find the PDF of S, what I will do, I will just take S is equal to this, and this will be cancelled with this, and you get W. So integration of W with respect to dW will be W squared by 2. Okay, so you get this. I think this is a simple integration, right? So S, so S is this. Now what is ds by dr? If I take the derivative of this, it's again just 2r, right? Okay, so dr by ds, in order to put it in that equation, this equation, if I take this, put it here, I will get cancelled and get one.
What do you mean continuous?
Continuous one?
Continuous.
Yeah, continuous is the original image. Like what you are seeing, this is continuous. It does not exist actually. I mean, discrete is like the one that we see on the computers. The original ones are continuous, but the continuous things are just like mathematical. Yes. But let's say we have an image here. Let's say the practical example. I think it will give you a more good understanding. Okay, and what is the first step now? In order to equalize this image, what is the first step? Image. And for that, I will need PDFs, okay, or probabilities of each value. So this is what I do. Okay, so if I do this, I will get this is the histogram, right? For all the levels, you have 0, 1, and 7 and 2. Rest are not there. Okay, so you get this thing. So probability of 0 is how many we have? 0 is 18. So 18 divided by 36, our total becomes 1 by 2. Then 1 is 6 divided by 36. 2 is 2 divided by 36. The other are 0. And 7 is 10 divided by 36. Okay, so you get all these probabilities. Now use the transformation function. What was the transformation function? Yeah, so it is L is 7, 8, sorry. Okay, because we have the maximum number 7. So it can be 8. I just put all the expression on the S expression. So I just found first some of these CDFs. Okay, from this is because 0 is from 0 to 0. So it's just P of 0, which is 0.5. Then 1 is probability at 0 and probability at 1. Then this is 0, 1, and 2. Okay, and similarly this one, and once I get this, I put it in the expression and I get the, so once I get the values, I have to miss out. Okay, and I get the image. Yes or no? This is another example of the same thing, so I will not be able to, I think it's useless to do that. And this is again the same example, just revisit just to make sure that how equalization works. Because first we discussed this example, at that time I did not show you how equalization works. Yes, this has again histogram, this one I transform this histogram with this, and what is the equation? Tell me the equation. How we transform this to this? Minus 1 sum of, this is maybe call it k. Yeah, maybe I is equal to 0 to k. Okay, p of. Okay, so this is what I did. Okay, so I think this is just using calculation. This is a problem. Okay, so again, some example I told you, this is what we already did, and this is again the X-ray, and you can see after histogram the ribs are more clear, right? So. Again, this is a batting backbone. Yeah, so this is low contrast. Yes.
To write them in a better picture, because more exciting.
Not necessary. Not necessary. It depends. In this application, it's somehow better because you are giving some more clear picture, but not always. It has limitations. Not always the best. Okay? One of the method. So I'm just giving you the advantages of that, and I will give you the disadvantages. This is more. You see, this is concentrated, and this is. Okay. And this we have the high contrast. Okay. This is again an example. You can try it. It's very nicely written, so I think you can follow this. You have the pixel number of counts. This is the probability count divided by total pixel. This is CDF, and then CDF multiplied by the maximum, which is 7, and then rounding off will give you this. So let's say you want to do an example. I think you can follow this first step. Once you get this, it means what it means. 0 will be stay 0, and 1 will stay 2. They will go to 2. 2 will be 4. 3 will be 5, and similarly 5, 4, 5, 6, 7 becomes 7. So I can find 0 where are 0. 0 is not there. 1 is 2. So I can put instead of 1s, I put 2. Okay, then 4, then 5, then 7, and that's it. So whole this slides, 54 slides, we just take this. And in order to go inverse, you can take the inverse using the function. This is again different CDF. I think we already did this. Okay, this is now not always good. If you have lot of concentration here, this will make the CDF more sharper here, right? Like this. And if I use this as transformation, I make it more brighter. So what I need, so maybe I need another curve which is very close to it, but not as sharp as this. Okay, something like this. So which should match, or something like this. It should match this, but it should not be as sharp as this one. Yes or no? Yes. Okay, so no, what we have our own histogram and try to equalize using that. So we call it histogram matching. I take the histogram on my own and try to map that histogram to my. Yes. The problem is that you see, if I do the equalization for this image, which is very dark, it will give me very bright. And the problem is because of the CDF, which is very sharply increasing at the start because of this dark image. So if I do this, it means that most of the image pixels I am making it very bright. So I need something in between. Okay, I need something similar but not as sharp increasing. So I will just follow the same curve but not as sharp as this. So this gives us another topic, which is histogram matching.